So I happily took Ahmed's suggestion to talk about this paper I wrote with Raphael several months ago. But I'll also be talking about some related work in progress also with Raphael. Yeah. Okay, so let me start with the page curve of an evaporating black hole. So if we think that the area of the black hole divided by 4G is a count of the number of degrees of freedom that the black hole is made of, we think that after the Spacetime, the Neumann entropy of the radiation differs significantly from the semi-classical prediction for the Neumann entropy. So here I'm making that distinction with the notation borrowed from a paper by Shahbazi-Moghaddam and Maldacena, where I show the exact entropy by S of boldface R and the semi-classical entropy as just S of R. And then H curve makes that distinction clear. After the Spacetime, this S of R differs from S of boldface R. Now, one way to state what's happening here is that the interior after the Spacetime is that the interior of the black hole is region I prime. Its entanglement in the semi-classical state with the radiation exceeds the area of its boundary divided by 4G. Now, when that happens for region I prime, I call the region hyperentangled. A convenient way to express the hyperentanglement condition is in terms of the generalized entropy. Remember, the generalized entropy of a region is the sum of the Neumann entropy of the region plus the area of its boundary divided by 4G. In terms of the generalized entropy, the hyperentanglement condition is just a condition that the generalized entropy of I prime union R is less than the Neumann entropy of R, all computed in the semi-classical state. So in the black hole context, hyperentanglement implies the deviation between S of boldface R and S of R. Now, we understand now the quantum extremal surface prescription gives us a formula for computing S of boldface R. Which involves regions called islands, which extremize the generalized entropy of I union R. A related quantity to quantum extremality is the quantum expansion, which I'll just review here. Given some region, we can define the quantum expansion by defining first orthogonal null vector fields on its boundary. Here I've shown K and L, where K points outwards and L points inwards to the region. And then the quantum expansion in the K and L direction are simply up to some normalization. It's just a derivative of the phenomenon of the generalized entropy subject to deformations in the K and L direction. And the condition of quantum extremality, in particular, is equivalent to the same and least quantum expansions are zero. Now, quantum expansions are in general difficult to compute because the Neumann entropy in the bulk is difficult to compute. But in the context of black hole evaporation, people have done this computation in many simplified models or toy models or with simplifying assumptions. And they do indeed confirm that in evaporating black holes, roughly speaking, after the interior becomes hyperentangled, you get an island, and that leads to a bound roughly like this. Upper bound on the boldface entropy S of R, S of boldface R. Now, since we sort of expected this, a bound like this, from more general consideration, starting from a hyperentanglement condition, and those considerations didn't really rely on a specific model or some simplified assumption, it would be sort of appealing to have a more general way of arriving at the existence of islands from a sort of easier to check condition like this. So that would be a little too quick because hyperentanglement in general doesn't imply an island. The basic examples of this are, for example, here where you have an Oppenheimer-Snyder type geometry of a collapsing star. And if the star has a lot of entropy, we can purify the entropy with the reference system. And in the interior of the black hole, I can find the region I prime that encloses all of the star. But if I push the region I prime toward the singularity, the area of its boundary could become very small. Therefore, I can make I prime super hyperentangled. But I don't expect an island here. Another even more basic way to do this is to just take a lump of matter and purify it to some reference system in Minkowski space and enclose the blue stuff with some zigzaggy in time sort of surface that stays almost null to decrease its area. And again, I can get a region that's super hyper entangled, but don't expect an island there. So this is the premise of the island finder. So you just find a set of natural, simple conditions that would imply an island. So this is how the setup goes. Take some reference system, quantum mechanical, non-gravitational distance system R, and some region in your gravity in the bulk I prime, such that I prime is hyper entangled. And in addition, it satisfies these particular signs and its quantum expansion. So the quantum expansion of I prime union R is greater than or equal to 0, because theta K of I prime union R is greater than or equal to 0, and theta L is less than or equal to 0, or the opposite side. Now, in this case, this is called the quantum normal region, and this other one is called the quantum anti-normal region. But anyways, the claim is that these conditions imply that there is an island, or in other words, the island is not the empty surface, it's not the empty set. And further, the phenomenon, the entropy of boldface R computed with the island rule is upper bounded by the generalized entropy of I prime union R. Now, the argument for this is really simple, but I just wanted to first take you through the assumptions that go into the argument. So the first and most important assumption in this whole talk is the quantum covariant entropy bound, or the quantum Busso bound. And just says that if you start with some partial Cauchy slice B1, whose quantum expansion in the L direction is less than or equal to 0, the generalized entropy of B2 will be less than or equal to generalized entropy of B1, where B2 is defined as the intersection of some future Cauchy slice with the domain of dependence of B1. So B2 is roughly the surface region I get by sliding B1 up this null hypersurface. Now here I've shown the transverse profile of this null hypersurface, and it consists of, this is the future boundary of the domain of dependence of B1, and it consists of orthogonal node geodesics shot out of partial B1, and they terminating them at caustics and self-intersections. So this hypersurface in general, some messy shape. So this assumption would follow from the following two things. By assuming the quantum focusing conjecture, and further assuming that losing generator does not increase generalized entropy, we can get this assumption. So let me just unpack that a little bit. Quantum focusing conjecture is the statement that the quantum expansion cannot increase as I go up the null hypersurface, which combined with this means that as I go up these null generators, the quantum expansion, generalized entropy decreases. But technically at these intersection points, at these caustics, the quantum expansion is ill-defined. So then we combine it with this other assumption that generators does not increase, that losing generators, as I slide from a surface, for example, here to a surface here, the generalized entropy does not increase. Okay, just a little bit of words on why these assumptions are natural. So quantum focusing in the classical limit reduces to the classical focusing, which is, for example, in GR implied by the null energy condition, and it's the basis of a lot of GR theorems. And the condition that losing generators doesn't increase area is just true. And quantum focusing in the non-gravitational limit implies a quantum non-energy condition, which is a non-trivial lower bound on the energy density in quantum field theory, for which we have various proofs of by now. And more importantly, maybe in full-on semi-classical gravity, the combination of these two assumptions going to, for example, proving the generalized second law, which Aaron Ball independently proved a while ago. And also in the context of ADS-CFT and subregion duality, the combination of these two assumptions very importantly lead to things like to consistency conditions within subregion duality, like the statement that the causal wedge of the boundary region is nested inside its entanglement wedge, or that two nested boundary regions have nested entanglement wedges. So because of these reasons, I wouldn't want to mess with these assumptions. And they would imply the quantum, and it's the quantum covariant entropy bound that's sort of being used here. you're careful. Okay, the second assumption is that there exists a Cauchy slice sigma on which the island minimizes the generalized entropy. So this condition. Now this condition would follow from the quantum maximum prescription, which was argued for in this paper, the realization of Aaron Hall's classical maximum prescription, which is supposed to be a prescription equivalent to quantum extremal surface prescription, where you pick all Cauchy slices, minimize generalized entropy on each slice, and then maximize over choices of slices. And because of the second step here, that implies that. When I have a Cauchy slice that satisfies this property, I call that Cauchy slice a maximum Cauchy slice. It's general, not unique. Okay, so here's the argument, this basic argument. Given a region I prime that satisfies the condition of the island finder, this either sign condition implies that there exists a null direction both to the future and the past, along which the quantum expansion of I prime is negative or not positive. By following that to a maximum surface, I find region I prime tilde, which satisfies this bound. That's because of quantum covariant entropy bound. And then because of sigma being a maximum surface, the second condition holds that the generalized entropy of I union R is less than or equal to generalized entropy of I prime tilde union R. Okay, now suppose that the island, so the choice, in principle, the choice of island is always the empty set. Suppose island was the empty set, then this chain of inequalities implied that S gen of I prime union R would be greater than or equal to S of R. Your contradiction with the hyperentropic condition for I prime, therefore implying that the island is not the empty set, and furthermore through this chain of inequalities and the fact that S of R is given by the island rule, S of R will be upper bounded by the generalized entropy of I prime union R. Now, just to see a few examples of this. First, let's do the non-examples from before. So why was it okay for these hyperentangled regions not to have an island? They don't satisfy the sign conditions. For example, in the star example, theta k and theta L are both negative. In the Minkowski example, they have variant signs along the transverse direction. Now, pretty basic set of examples are when your spacetime has a single time symmetric slice. And then the thing just reduces to the statement that hyperentanglement just implies an island. Now, the only reason I bring this up is to just emphasize that to get hyperentanglement to imply an island, you need to involve the time direction in some sort of non-trivial way, either in the choice of your region or in the dynamics of the space-time. And that's probably just more broadly related to understanding the max part of maximum from the boundary, or just understanding the time direction in the bulk in general. Okay, now examples of this time symmetric case are very abundant. I won't go into detail, but you can have these monster solutions where you do a large volume region behind a small throat black hole horizon, all on a time symmetric slice. And there could be a lot of entropy here. And you purify it with the reference system, you get hyperentangled regions. Also similar conceptually examples in cosmology. But let me just cover the example of evaporating black hole a little bit and just show you why the condition of the island finder can be verified without trying hard or relying on some simplified assumptions. So the hyperentanglement condition is basically just the definition of the page curve. So just to be safe, let's go a little bit after the page curve so that we can be sure that this condition is satisfied for I prime. Now let's shoot for this set of condition, the quantum normal condition. Near the horizon, the quantum expansions receive important corrections from the derivatives of the phenomenon entropy. That's, for example, because in the theta k example, area variations in the k direction become small near the horizon, so they start competing entropy derivatives there. So one way to not have to worry about that, worry about basically having control over the phenomenon entropy derivatives, is to bring I prime a little bit outside of the black hole. And a bit outside of the black hole, the classical terms would dominate. So the theta K and theta L would just be dominated by the classical values, which is just a statement that the variation of the area in this direction is positive and in this direction is negative. So that's it. That's one way to satisfy these conditions, and then you would imply the existence. That implies the existence of islands, subject to the assumptions. Now, this is bringing I prime out is that it costs us the area term being large, and it therefore doesn't give us the best upper bound here. So just, for practical purposes, I'll show you how one can try a little bit better. So we can put, for example, put the boundary of I prime on the event horizon and rely on the generalized second law to give us the sign that theta K of I prime union R is greater than or equal to 0. Now the area variation in the L direction is still large negative. Now with the benefit of hindsight, we know that as you move to the past along the horizon, at some point where the area radii between the boundary of the past of R and the horizon gets small, like well, this delta R becomes order G, for example, that gives a scale to the entropy derivative computation, which gets it to be able to compete with the area variation in this direction. So by just picking some large number C1 to create a separation of scales, which amounts to pushing I prime a little bit to the future at this point, we can suppress that effect and again get from the classical area shrinking in the L direction that this condition is satisfied. So that tightens the bound a little bit. So that's basically all I wanted to say about the island finder. I mean, I find that it's sort of conceptually interesting, but I wanted to show this example just to point out that, it might have some practical application. I mean, if you're looking for islands, chances are this would be a good first try. Okay.
Sorry, what is the red curve?
The red curve?
Yeah.
Red curve is like the line where the area radius here and the area radius there is of order G. So at some point it hits it goes inside the horizon and it continues going behind it. Going fast. This is basically, okay, so again, I'm going to shift gears to talk about some work in progress with Raphael on proving a new singularity theorem. So our singularity theorem has a lot in common with Penrose's singularity theorem, just structurally. So I'm going to give you a brief review of that first. And so the ingredients that go into our singularity theorem are sort of related to the first half of the talk. Okay, so Penrose's singularity theorem is in a class of singularity theorems where the definition of a singularity is the existence of an incomplete null or time-like geodesic. That's a geodesic where starting from some point in space-time, it has no other endpoints either to the future or the past, but only a finite range in affine parameter for proper time. So here's an example of two such geodesics. Now here, suggestively, the incompleteness is being caused by the curvature singularity, but more generally, these theorems don't tell you about the origin of the incompleteness. They just tell you that there exists an incomplete geodesic. Okay, so let me just give you a brief review of a sketch of a version of Penrose's singularity theorem. So this is the classical singularity theorem. I'll talk about some classical generalizations after. So the setup is consider a non-compact partial Cauchy slice I prime whose boundary is a compact smooth submanifold which satisfies the following classical expansion, just the area derivative sign that areas in the L direction where L is the null inward direction, null orthogonal inward direction to I prime. The theta L is less than 0. Now in this picture, I've shown two pictures of I prime here. Because of drawing purposes, I've shown I prime looking like a compact region, but you should imagine that I prime is not compact in this picture. Okay, then the statement is that at least one generator of L, the future boundary of the domain of dependence of I prime, is incomplete. So here I've shown L, these two pictures. Really roughly, the way the argument goes is that you first assume that no generator is incomplete. combined by Ricciarduri's equation and classical focusing, is initially contracting null congruences reach focal points within a finite range in affine parameter, past which they cannot be part of L. So in this picture, I've drawn one simplified case where they all go to the same focal point. And that ends up implying, together with the fact that boundary of I prime is compact, that L itself is compact. But that gets to the following contradiction. By following time integral curves of a smooth time-like vector field in the space-time, I can map L to sigma homomorphically. And since L is compacted and on its only boundary is partial I prime, L would have to map to all of I prime. But that's a contradiction because I prime is non-compact and L is compact. So roughly speaking, this is a statement that I prime cannot time evolve to L. Okay, now this was a classical theorem. It's important when possible to generalize this theorem to the semi-classical case, because for example, Penrose's theorem is violated in the presence of an evaporating black hole. The counterexample. So this was done beautifully in a paper by Aaron Wall several years ago, where very naturally, the conditions stayed all the same, except the classical expansion condition was replaced by the quantum expansion of I prime in the L direction. And by swapping classical focusing with the generalized second law, Aaron Wall was able to do the same result. Now we're going to do the same. I'm going to present to you a new classical singularity theorem, and then just state the quantum version and discuss. Okay, but let me remind you I'll tell you about the central assumption of the classical singularity theorem, which is the classical covariant entropy bound for the original Husserl bound. And the statement of that is starting from some surface mu. If you shoot out a null hypersurface orthogonally to mu, such that call that L, such that L is nowhere expanding to the future of mu, then the entropy crossing L is less than or equal to the area of mu divided by 4G. So this, in some appropriate sense, is the classical limit of the quantum covariant entropy bound, but I won't get into that. Okay, so here's the similar new singularity theorem. Let I prime be now any partial Cauchy slice, compact or non-compact, such that its boundary is a compact, smooth submanifold, partial I prime, such that the following these two conditions hold. As before, theta L of partial I prime less than 0, but now add this additional condition that the entropy on I prime is greater than the area of the boundary of I prime divided by 4G. Now the conclusion would be that at least one generator of L, again, is incomplete. The way it goes, similarly to Penrose's case, we conclude that if there's no incomplete generators, that L is compact. So that gets us into contradiction with I prime being non-compact right away, as before. We're using a case to I prime being compact. But then the implication would be that the domain of dependence of L and the domain of dependence of I prime are the same, as should be intuitively clear in this picture. Then that, together with condition 1, implies that the entropy on L is greater than the area of the boundary of I prime divided by 4G, which contradicts the covariant entropy bound, because L is a light sheet by classical focusing. Okay. Just to show you some examples of this classical singularity theorem. Again, bring back the example of the star. This region I prime in the interior could have a lot of entropy of the star, the entropy that exceeds the area divided by 4G. And the expansion, classical expansion in the L direction is negative. And that singularity is being predicted, or an incompleteness in that direction. And that's to be juxtaposed with Penrose's theorem, which can only be applied to the complementary region, which is non-compact, and would predict the singularity in that direction. So perhaps this compactness, the freeness of the non-compact assumption is actually one of the important features here. This particularly could be useful in spatially closed universes. But Penrose's theorem never applies. For example, consider a closed FRW, radiation-dominated FRW universe. So these slices are spheres. And at some early time, I can find a region I prime that satisfies the conditions of our theorem, predict a Big Bang. And here's another example that Raphael likes to talk about. Consider the Sitter space. Now, the Sitter space doesn't have a singularity. It also doesn't satisfy the conditions of our theorem. But by moving I prime very late to the future, you can make the volume of I prime grow really large, larger than the area. Like I prime grows more rapidly than the area as time goes by. And then you can put a dilute amount of radiation with a dilute amount of radiation on I prime, meaning that you can put the radiation dilute enough that the back reaction on that late slice could be negligible, while satisfying the conditions of our theorem, because the volume is very large. And then one predicts a Big Bang this way. Okay, so this seems like a natural classical theorem, and I'm just going to present you with the quantum version of this theorem. So the statement for I prime is as before, except now the condition 1 is being replaced by the hyperentanglement condition. So, and the quantum classical expansion sign is being replaced by the quantum expansion of L in I prime union R being less than 0. So in some sense here, the non-compactness condition is being swapped with the information theoretic condition, the condition of hyperentanglement. So one can derive the same conclusion can be derived by combining ingredients from the past 3 singularity theorems. Including assuming the quantum covariant entropy bound. Okay, so this seems to be really the natural 4th singularity theorem in the chain of the past 3 that I mentioned. Okay, but now I'm just going to, in 1 or 2 minutes, the next 1 or 2 minutes, I'm just going to conclude with some sort of features and puzzles that this is the us do. I should warn you that beyond this point, I'm not very certain about everything. Okay, for example, take the Reisner-Nordstrom, the Harlow-Harkin state in Reisner-Nordstrom geometry, and pick regions R to be these ones, and I prime to be a long region in the interior, such that I prime is basically after the page time. Then the hyperentanglement condition is satisfied, and the quantum expansion, I prime satisfies the conditions of the natural quantum singularity theorem in the little L direction. But in the classical geometry, at least, nothing is preventing the domain of dependence of L from closing up. There's no completeness in that sense. Now, of course, we're familiar with the fact that in Reisner-Nordstrom, the inner horizon is unstable to arbitrarily small perturbation from the outside. So that could cause a singularity. But perhaps more relevantly here, there is some work suggesting that the semi-classical, just computing the expectation value of the stress tensor in the Harlow-Harkin state on the inner horizon results in a singularity. The stress energy tensor is singular at the inner horizon. And that would have a large semi-classical corrections to the geometry. Now, more work needs to be done to confirm whether that was being predicted by the singularity theorem or not. I don't know. The more puzzling example is that the conditions of this quantum singularity theorem are being satisfied after the page time in an evaporating black hole in the opposite direction of time. Now, I really don't know exactly what's going on here, but I just will say some words. In simple toy models where you can just compute the generalized entropy and follow your nose, it seems like As you slide the slice, these pink slices down while computing I union R, the generalized entropy of I union R, the quantum covariant entropy bound remains satisfied basically all the way to the end. And it's that very last bit where you reach a caustic and I goes to the empty, and this pink region goes to the empty surface, goes to the empty set, that at that point, there seems to be a violation of the quantum covariant entropy bound. But there's something weird here. It seems like at the heart of this contradiction, of this violation, is the statement that these small pink regions in the past nevertheless purified all of the Hawking radiation here in the form of highly blue shifted interior Hawking modes. Now, that doesn't sound very semi-classical. So one possible sort of vague thought is that maybe there is a sort of a consistent semi-classical prescription that informs us that one has to stop assigning generalized entropies to these pink regions union R if we slide too far in the past. So such a semi-classical restriction would, for example, that would be sort of a new notion of incompleteness that's just based on the fact that these slices should not be assigned generalized entropies to. One way to see this, for example, is to look at the complement of I union R, which is these slices that start from here and go all the way to that, these endpoints. And those slices are in some sense getting really boosted, highly boosted. So maybe at some point one has to stop assigning generalized entropies. And that's the incompleteness that's being predicted here. But it's fair to say I don't completely understand what's going on here. I'll be happy to talk more with anyone who's interested, but also encourage you to talk to Raphael about this if you're interested. He seems to have some bolder thoughts on this. Thanks.
Questions for Arvin or Raphael?
I have a couple of questions. So first, Penrose's theorem assumes global hyperbolicity.
Yeah.
All of your theorems are also
Yes.
doing that. I mean, it would be nice to relax that so we can do this in ADS.
You mean ADS without focusing on it, going to a Wheeler-DeWitt path?
Yeah.
I wouldn't be surprised by a generalization like that.
Yeah. I mean, already I know the classical Penrose singularity theorem has been generalized.
Okay.
To ADS, so, but yeah.
Yeah, I haven't directly thought about it, but I think I'll be surprised at this one.
Yeah. So, but I mean, also for your Reisner-Nordstrom example, I mean, where you say, like, even classically, the way that doesn't evade Penrose's theorem because the globally hyperbolic part of that spacetime is incomplete. So
no, but Penrose singularity theorem would be
because there's a Cauchy horizon.
Yeah, but yeah. So I mean, the applications are different. Penrose's theorem would apply to this exterior region, to the complement of I prime, because you need the non-compactness assumption. And with this, the incompleteness that would be predicted. Well, if let's move I prime a little bit to the interior, so its expansion in that direction becomes negative. Then the incompleteness that would be predicted in Penrose singularity theorem in the globally hyperbolic spacetime is just a Cauchy horizon.
Right.
So this thing is, since I prime is compact, and that's actually kind of an interesting feature here, you don't hit the Cauchy horizon. You move in this direction, and the incompleteness is to show up in this direction.
I see.
So that's.
I see. Okay. And can I ask just one more quick question?
Yeah.
So in the first part of your talk, I mean, one implication of your island finder is that a quantum trap surface can never be the boundary of an island, if I understand correctly. Your island finder says it has to be normal or anti-normal.
Quantum trapped as you mean?
As the boundary of the island?
Quantum trap is a sign condition on the quantum expansion. If it's the quantum expansion of I union R that you're talking about, then yes. But that's obvious because the trap surface just manifests these in the extreme.
I think you may have misspoken when you asked the question. Obviously, a trap surface cannot be the boundary of an island. The question was going to be the boundary of a different region from which we can infer the existence of.
Yeah, okay.
Oh, yeah, that's what you meant. Yeah, I mean, I prime is in general, not the island itself. I prime
Okay.
some region.
Okay, sorry, yeah, I understand. But I mean, that sounds like an interesting statement, or maybe it's obvious. I don't know. Just saying that islands are excluded from being too close to the singularity, or
The island finder doesn't tell you very much about how far away the island is.
Yeah.
It's just, Arvin was just exhibiting an example of something that's hyperentropic and doesn't allow you to infer the existence of an island.
so we can't deduce something about where islands are or aren't from this.
Not from this,
I see.
because this is very agnostic about where the island is.
I see. Okay.
Detector, not finder.
That's.
Sorry.
Put out a V2.
In the Riesenröhrchen puzzle,
Yeah.
I'm confused which of the inputs of the theorem breaks down if you just stare at this semi-classical picture. Why didn't it work?
Well, the semi-classical picture, presumably in the semi-classical picture, you need to compute the expectation value of the stress tensor, right? On this geometry. And the claim in some of these papers is that diverges in the inner horizon, in the Harlocken state.
Is there so in the other puzzle, there was a very highly boosted surface?
Yeah.
Is there also a very highly boosted surface playing a role here in the Riesenröhrchen?
Maybe, but fundamentally, I think the previous puzzle is that when you move down, these interior modes that are purifying the radiation remain on your slice. So that they get highly boosted. But as you go up in that direction, I think you will lose this purification. So it seems a little bit conceptually different from that. But maybe they reduce to the same statement. I mean, there might be a highly boost. Well, think about the complementary region. Maybe what you're saying is that as you move this down or up, the boundary and anchor a surface to that boundary and this boundary, that somehow gets highly boosted.
Let's see, to answer his question, I think one thing that breaks down is the covariant quantum Busso bound, I think. Well, I mean, the generalized entropy at this point becomes very negative, right? When it's very small.
Mm-hmm.
And then when you go beyond the point where they touch, it becomes...
Is it, you think that this would happen in this, you're just saying any small region would have a...
I think that's what happened. Well, I look more at the other case that I think that's what happens.
Yeah,
but in this case, I think it's likely that something...
So the entropy of which region one?
It should be a small region here, union 1.
Well, I'm familiar with the other. Can we go to the other one?
Yeah. Well,
I think it'll happen.
So in this case, the assumption that what happens is that the generalized entropy goes down and becomes very small at the very tip at the bottom. So the assumption was that you can continue, you can go to a slice which is a little bit below, right? Below that point.
Yeah.
And that the generalized entropy will continue to decrease, right?
Well,
and it actually increases. It goes back to being R, right?
Yeah.
So that's the assumption that's breaking down.
Right? But I mean, in this case, I fundamentally tie to the fact that when you slide this below this point, you lose these purifications of R.
Yeah. Well, I mean, that's the explanation, but just going to answer.
Okay, it's this thing that I'm not. Okay, maybe we should talk about it afterwards. But it's this particular feature that I'm not seeing as clearly here. I understand that the regions are getting small.
I had another comment about the other one. So
which one?
Can we go to the next slide?
Yeah.
So here, if you decouple the radiation, and you evolve backward, there will be a shock wave that goes back, right?
That's right.
That feature makes it similar to the previous slide in the sense that there was some singularity very close to.
Exactly. No, that's right. So there is. I mean, in this state, if you generically perturb I prime, you will cause that singularity. And these distances here are like sub-Planckian. So You're connecting it to the instability of the inner horizon?
Well, not directly, but it's similar in the sense that there is a singularity that is potential singularity that is close to the surface you're considering.
That's true. It would be, yeah. So technically, it's causally separated from that point, but it's not completely clear if you should talk about that distance as being a meaningful separation. So maybe the singularity is right here. But yeah, this is, I would say, is being investigated. Maybe that's what the singularity theorem always points to, is that the singularity is nearby in that sense.
I guess I want to just comment on that. I think it's sort of very tempting to think that this has something to do with just running the evolution backwards without the radiation, or even if you made a small mistake in the radiation and you don't run it exactly backward. But I think there are two issues with that. One is that the singularity does appear in the wrong place. We need it to appear not on the path boundary of R, but further in at somewhere around the horizon. And secondly, I just don't see why we wouldn't be allowed to just run it back as shown in the picture, and just simply reverse the semi-classical evolution that happened here, and that still leads to a puzzle. But with regard to something else that one said, I think it's clearly a feature in a lot of these situations that the generalized entropy formally becomes negative, and then we probably shouldn't assign it. But this is true in many completely harmless situations where we need something like the quantum covariant entropy bound to be valid to prove things like strong subjectivity using maximism, things like that. These are all, I think, important observations, but at least I think we can say that we haven't been able to turn them into a criterion for excluding these slices, in particular the very last one where you do know how to compute the generalized entropy, where you dive below the event horizon. And the top one, you can just apply the bound to this pair of slices. And it's very hard to come up with a criterion that would exclude that from the scope of the bound without getting rid of a lot of important structure that we need elsewhere.
Yeah. Just to connect it a little bit to something I was saying earlier, the assumption that I said two things imply the quantum covariant entropy bound, that losing generators does not increase the generalized entropy. And this is the thing that's in trouble here. But losing generators is completely generic in every application of the QFC that we think of generically. We have that. So it's not the one who moves that.
I mean, here you're losing generators and the generalized entropy is going negative for some reason. Normally, I don't think that happens.
Well, yeah,
it's not a generic.
It does. I mean, as soon as some gap becomes small, it goes negative. And the loss of generators is generic. I mean, almost any cut of a null surface will continue endpoints of generator.
This negative thing is just that the log becomes negative if you look at L.
Yeah.
But aren't you like somehow using the wrong cutoff at that point when you're concluding that? Because you're saying L is much smaller than your cutoff.
I don't think the mistake is in the cutoff. I think the mistake is in making the length smaller than the fixed cutoff.
Sure, but you can always start with a smaller cutoff to start with. Like you make it like super exponentially small. Then you have to introduce a large negative counter term in the beginning to get the right answer. And you'll still, that counter term will then still make the entropy go negative, no matter how small you chose the cutoff. Because the thing that you have control over is the quantum expansion. You just integrate it up. So no matter how you turn it.
And I would like to ask Raphael to share some of his bold.
I on purpose kept it short.
All right. So, I mean, I think we've seen sort of schizophrenic things in semi-classical evolution before, right? When we look at the famous island calculation, we're doing a calculation in a semi-classical space-time where if we compute the out state directly, as Hawking did, it's mixed. If we compute the entropy directly, as some people here did, you find it follows the page curve. So I think this is another example where this picture just, gives you different answers depending on which question you ask. And one way to resolve this conflict in the example I just mentioned, which may not always work, is to invoke an ensemble, to say that gravity computes an ensemble average. The average of the state is mixed. The average of the entropy, every theory is unitary, is the page curve, self-averaging. In that kind of setting, you would not expect time reversal to apply. Forward evolution would prepare the average state on this future slice, and when you run that backwards, in most theories, you're not going to reverse the state correctly, and you will in fact get these kind of errors that can cause singularities to form. So that's my fantasy about how this might tell us something more about how gravity is really on its own.
Thanks a lot, Raphael. So let's thank Arvin and Raphael.